Hi everyone, this is Shubham. I work at NVIDIA as a software engineer. People often ask me how they should go around learning computer vision, where should they start, how important are the classical computer vision algorithms, etc. To be honest, I am not an expert. I am still figuring things out myself. However, in my opinion, having a good knowledge of the basics always helps. Building projects using classical computer vision algorithms can be really helpful in building intuition around fundamentals of computer vision. Because I think learning theory is one thing, but using concepts in applications is a completely different thing, and building small projects using what you learn in theory can really bridge the gap. So I had done one project while learning computer vision, that is Panorama's teaching. This project really helped me in understanding concepts like feature extraction, feature matching, homography matrices, image warping, and RANSAC algorithm, etc. So today I'll be discussing that project in some detail. I will not be discussing each algorithm in depth, but I will be providing resources which you can refer to learn about these algorithms in detail should you choose. In this video, I will give brief description of the techniques, and I will try to explain how everything fits together. So let's jump right into it. So the problem statement says you are given a set of images of a scene taken from different viewpoints from the same camera, where each image has some part of the scene visible. Now stitch all these images into a single image to form the complete image of the scene. So there are few points which are very important. First is all the images should be captured using same camera. So we really don't have to worry about the camera intrinsics. Second one is each image should have some overlap with the image to which it is to be stitched, right? So that's basically because we need some common points in the images. So this part we will be discussing later in the video. So on the screen you can see these two images. So the first and the second one. For example, we have these three images. These images are taken from the same camera and are of the same scene, but different camera viewpoints, right? So we should be able to merge these images and should get something similar to this one. The boundaries of the stitched images are not smooth. That's because the blending algorithm is not part of the pipeline yet. Now that we have seen what we will be building as part of this project, here is the list of all the algorithms we will be using. SIP for image features, extracting image features, BF matcher to match the features, and we'll build a homography matrix using the correspondence points. Then we'll be warping one image to the camera frame of the other image. Then also we'll be using RANSAC at some point to uh, sample points to get the best homography or the better homography matrix. We will be discussing them in more detail in their respective sections. So I'll start with importing all the packages that I'm going to need for this. Then I will load the images, input images, and simply plot them. So first thing that we are going to do is extract features from the input images. So I'll be using SIFT algorithm. SIFT stands for Scale Invariant Feature Transform. So, so features are the properties which makes an image unique, or using which we can identify an image. So while using the SIFT algorithm, we get the key points and the descriptors. Descriptors are nothing but uh, for each key point we will have a vector. So these descriptors or these vectors will be used by our matching algorithm to say uh, which two features are similar, right? Now that we have extracted the features from both the images, next step is to match these features. For matching the features, we are using brute force matcher with L2 norm distance. So what we are doing is matching the feature descriptors of image 1 to the feature descriptors of image 2, and then making pairs based on the closeness of the descriptors. In our example, we will only keep closest 20 matched features. These features or key points will act as correspondence points while calculating the homography. So here we are using norm2. We are passing in the descriptors of both the images, and then we are sorting based on the distance, and we are keeping closest 20 matches. We can also draw the matched key points using this CV2 method, and this would give us both the images side by side, and the key points, matched key points, will be matched using a line. So for example, this point corresponds to this point in this image. Now that we have the correspondence points, we will calculate the homography matrix using those correspondence points. We need the homography matrix to transform the image 2 to the image 1's coordinate frame. To do that, we will need homography matrix. I have provided the link to a good video and a slide to understand more about homography and how it is calculated. For our example, the essential thing to know is homography matrix is the eigenvector corresponding to the smallest eigenvalue of A transpose A, where A is constructed using the correspondence points. So if you look at here, it is basically constructed using the correspondence points, and it has shape 2 into n, where n is the number of correspondence points, and it has 9 columns. So to understand the construction and why we are using this correspondence points, I would really recommend you to watch the videos. So once we have created the matrix A, we will calculate the we will use SVD decomposition to get the eigenvector corresponding to the smallest eigenvalue. So now that we have the homography matrix, we will use this matrix to warp the image to image 1's coordinate frame. So after calculating the homography matrix, we can use the homography matrix to work the image 2 to image 1's coordinate frame. But first we will need to create a target image big enough to accommodate both the images. Then we will first copy the image 1 to it without any transformations, because we intend to transform image 2 to image 1's coordinate frame. Then we will use the homography matrix to uh, transform image 2 to image 1's coordinate frame. So this piece of code here is a efficient way of writing this piece of code. So if you look at this piece of code, we are converting each pixel location to homogeneous coordinates and transforming it to using homography matrix, uh, and then removing the homogeneous coordinate by dividing both the points using it. And then we are copying the image 2's pixel to final image based on the transformed points. You can also visualize the target image. So in the first step, when we only copy the image 1, this is how our target image will look. So it only has the contents of image 1. Then we also stitch the image 2 using our code here and save it to target image and visualize it in here. So now you can see the contents of image 2 are stitched to image 1. So one thing you note here is these black pixels. So this is basically the flaw of forward warping. So in the notebook we are using forward warping, but in the Python script, which I will show you next, has the provision of backward warping as well. Now that we have stitched the two images together, I am leaving it as an exercise for the viewers to stitch the third image of our example from the notebook. Should the users have any problem, should the viewers run into any problem with the exercise, they can always refer to this Python file which I am showing on screen, and I will share the link of the GitHub repository in the description. The changes between this Python file and the Jupyter notebook are basically inclusion of RANSAC algorithm and backward warping in the Python file. So I'll quickly go over the RANSAC algorithm. So we are using RANSAC algorithm to sample, which is the backward warping homography, as I had discussed, by using a subset topping that is the existence of, and we sample pixels in the homography matrix target image. The out of in backward warping we trials whichever matrix different aligns more. So in forward warping we will transfer highest number of points the pixel values from image 2 to image 1's coordinate frame. But in here we will do it other way around. We will just take the pixel values of image 1's coordinate frame, and using the inverse of homography matrix we will black transform them to image 2's coordinate frame target image. So this way we will make sure that there are in backward warping we do the pixels in the image 1's coordinate frame. So in forward warping we were transforming the pixel values from image 2 to image 1's coordinate frame, but in here we will do it other way around. We will take the pixel values of image 1's coordinate frame, and using the inverse of homography matrix we will transform them to image 2's coordinate frame. So this way we'll make sure that there are no black pixels in the image one's coordinate frame, or rather image one's coordinate frame's target image. So that's it for this video, and I hope you could take away few things from this video. There are a few things in this Python file which I have not discussed, and I would really encourage you to go through this Python file, maybe give it a try, run it, and if there is anything which is not clear, do comment on the video. I'll give the link to the repository in the description. I hope you like this video. Thank you.